Hello, my name is Teixeira, and I'm a PhD student at Princeton. In this talk, I'll be presenting PacketScope, a system for monitoring the packet lifecycle within a switch. PacketScope is a collaboration with Rob Harrison, now at the US Military Academy, Arpit Gupta, now at UC Santa Barbara, and Jennifer Rexford at Princeton. So let me start by talking about why we want to peek into the insides of a switch. So modern switches, and especially programmable switches, are becoming complex devices that perform multiple types of processing on packets. For example, packets may have their header fields modified as they move through the switch. TTL values may get decremented, flags may be set, and even addresses and other fields may change. And this processing may occur in multiple pipelines, such as ingress and egress pipelines. Access control list rules might flag packets to be filtered and dropped, and queues can build up, causing packets to be delayed or, in the worst case, lost if a queue fills up entirely, which can significantly impact application performance. So ideally, we'd like to have a system that can reason about all these types of processing, and in addition, can provide network operators with an easy-to-use query language that allows them to ask questions about this processing and monitor the switch. Specifically, we looked at data flow monitoring systems, which provide a data flow language with operators like map, filter, and reduce that apply to incoming tuple data. In this case, tuples represent individual packets. Now, prior systems in this space either only captured packets as they first appeared when they arrived at the switch and ignore the switch pipeline entirely, treating it as a black box, or they provide some limited detail about the queuing experience of packets. But none of these systems look into the modifications done by the switch pipeline, nor do they look at access control list drops or queuing losses by the switch. So we decided to design PacketScope, a query language and system that allows network operators to monitor the full packet lifecycle, including packet modifications, access control list drops, queuing delays, and queuing loss. Now, let me talk about the query language of PacketScope and how it helps us represent the full life of a packet within a switch. So when a packet first arrives at a switch, the switch learns what port it entered on, its initial header values, as well as the timestamp. The packet then moves through ingress processing, where it may have its header values modified, and it may get marked for drop by an access control list rule. At the end of ingress processing, the switch learns the intended output port, as well as the values of the headers in the packet at that time. Now, we call this the intended output port because the packet might not actually be sent out that port. For instance, it may have hit an access control list rule on ingress processing, and so port intent would indicate that this packet is meant to be dropped and not queued. In addition, the packet might get lost if it tries to queue up in a full queue, or it may get marked for drop on egress processing. If the packet is successfully queued, it will eventually be dequeued and enter egress processing. And at that time, the switch learns information about the packet's experience in the queue, including the length and time when the packet entered and left. The packet then undergoes egress processing, where it may again be modified or marked for drop. And at the end of egress processing, the switch learns its final output port, or whether it's to be dropped, as well as the final values of the packet headers. Now, in order to represent packets as tuples, we created two types of tuples. The first are ingress tuples. Ingress tuples represent all packets that are seen by the switch and undergo ingress processing. Ingress tuples contain information about packets at the start and end of ingress processing. The second type of tuple is the egress tuple. And egress tuples represent all packets that are queued and enter egress processing. And those tuples contain all values about the full packet lifecycle. In particular, note that egress tuples represent packets that are not lost due to a full queue. So now let's look at an example query. Let's say we want to count the number of undropped SSH packets that traverse a network address translation algorithm. So we'd start by marking our query to apply to egress tuples, which are all tuples for packets that did not experience a queuing loss. Next, we'll add a filter that only looks at incoming SSH packets by checking the TCP source port. Then we'll check whether or not the packet traversed a NAT in the switch by checking whether the source IP of the packet changed from when the packet entered the switch to when the packet left the switch. And then finally, we'll add a filter on the output port to ensure that the packet is not meant to be dropped due to an access control list rule. Now let's handle the case of queuing loss. So when a packet tries to enter the queues, it does so after ingress processing has fully completed. That means that when the packet is lost due to a full queue, we don't have a programmable hook into the switch to capture the packet at the time it is lost. This makes it difficult to track individual packet tuples that experience queuing loss. However, over time, we can track aggregate counts of queuing loss by keeping state on the ingress and egress pipelines. So we introduce a lost operator, which counts packets grouped by a set of fields specified by the query and reports results every epoch milliseconds, where the arrival time of packets determines which epoch the packet is placed in. Now we'll discuss how we efficiently compile our queries to the switch processing. Our main compilation strategy is called tag little, compute early. The idea is that we try to tag packets with as little data as possible as they move through the switch, and we try to execute our queries as early as possible in the pipeline to free up resources later. So for example, let's go back to our network address translation filter, which checks whether the source IP of a packet changed from the in-field to the out-field. To execute this query, we have to wait until the end of egress processing to know the final value of the packet source IP. However, at that time, we also need to know what the original source IP of the packet was in the case it does get modified. The solution is to tag packets with metadata of their original source IP, so that as they move through the switch pipeline and the source IP may be modified, we still have access to the original source IP at the end of the pipeline and can execute the comparison there. Now let's say we have a query that compares whether the source IP changed only on ingress processing by comparing the in value to the mid value. In this case, we don't have to wait till the end of the switch pipeline to execute the query. In fact, we can execute it as early as the end of ingress processing, because this query only involves fields that are relevant to ingress processing. In addition, this allows us to free up the metadata we've stored so far so that it can be used for later query processing or later switch internal processing. Now we'll discuss how we compile the lost operator. So for example, let's say we have a query that counts the number of packets that are lost to the queue grouped by source IP and reports results every 10 milliseconds. So as we discussed before, we don't have a programmable hook to capture packets at the moment they are lost due to the queue. We can only place our query processing in one of the two pipelines. So our solution is to keep state about the number of packets that are seen at each pipeline and compile the lost operator as a join of two queries, one that counts packets by source IP on the ingress pipeline and one that counts packets by source IP on the egress pipeline. Then, every 10 milliseconds, we report the difference between these two counts by source IP in order to return the final result. The gory details of how this all works can be found in our paper. Now I'll discuss the PacketScope prototype. So PacketScope is currently implemented as an extension to the Sonata data flow monitoring system, with added support for queries that look at packet modifications, queuing delays, and also implement our tag little, compute early compilation scheme. We've also built a prototype of a queuing loss query using the BMV2 software model. More details of our prototype and evaluation, as well as our proposals for future work, can be found in our paper. So in conclusion, we designed PacketScope, a network telemetry system that uses a data flow programming model, allowing network operators to express queries about the full packet lifecycle within a switch, including packet modifications, access control list drops, queuing delays, and queuing losses, and compiles those queries efficiently to programmable switches. Thanks for watching, and as the world is currently fighting a pandemic, for those you love and for those you've never met, please stay safe and stay home. Thank you.